player piano is like a computer. Its music is programmed by inserting a roll of punched paper. As the roll turns, the punched holes trigger the keys and strings of the piano. A man is like a computer. He is programmed by heredity and environment. To the extent that he is creative, he is more than a computer. He is a form of life. But he is much slower. And he makes mistakes. This is a high-speed electronic computer. Like the piano, it too may be programmed with punched tape or cards, or by more advanced devices such as magnetic tape or teletype units talking directly to the computer. Like the man, it too does arithmetic. In fact, in 1 second, it can do far more arithmetic than the man, using a desktop calculator, can do in a full year. In 1 second, the computer can perform more than 1 million arithmetical operations. And arithmetic is only one outlet for its many talents, performed with electrons moving at nearly the speed of light. A computer can do research, analysis, and business management, can make decisions, can play cards and chess, and even compose and play music, like this. Without the high-speed computers which the manned space program helped develop in the 50s and 60s, there would be no manned space program. We could not have orbited the Earth. We could not have landed men on the moon. Let us see why. The environment of spaceflight is full of unearthly complexities. Intruders in space must cope with solar and cosmic radiation, with extremes of heat and cold. Meteoroids, weightlessness, vacuum, silence, and infinity. Before flying off into such a different environment, we require carefully designed spacecraft to carry life support systems of air and pressure. We must provide for food and water, waste disposal systems, protective structures, and energy systems for electric power and propulsion. Computers play an important role in the design, manufacture, and testing of all such systems. To minimize costs and maximize safety, spaceflight systems and requirements are first simulated by computers. In this way, for instance, hundreds of multi-million-dollar manned moon landings were made before the Apollo lunar landing spacecraft was built. For comparatively little, essential engineering data were derived and safety measures were tested without risking lives. In planning a spacecraft, some of the most important components designed are the onboard computers. This is because many of the solutions and decisions we face as we travel in this new ocean of space are beyond the problem-solving capabilities of men unaided by computers. For example, if we are orbiting the Earth or the Moon and wish to rendezvous and dock with another spacecraft flying several miles ahead of ours, large numbers of complex flight computations must be made almost simultaneously. To change our orbiting speed for rendezvous, computers are needed to fire the spacecraft's propulsion engines. To change our attitude for docking, they must fire attitude control thrusters, often in bursts measured in tiny fractions of a second. The rendezvous and docking maneuver is just one of many spaceflight phases containing far too many variables for a man alone to compute and apply in the time available. Computers, both on board the spacecraft and on the ground, are indispensable in keeping track of the details of spaceflight dynamics and navigation, predicting relative positions, and monitoring remaining fuel and other consumables, as well as firing thrusters and engines as needed. Long before a space mission is launched, the parameters of the mission must be calculated with the help of high-speed computers. Optimum design of the mission profile and the spacecraft can be predicted by the computer in advance using theoretical data. Scientists and engineers present their problems in the form of mathematical models to the scientific computing specialists or computer programmers, who translate the math into computer language. This coded math is punched on cards as instructions to the computer. Also, data related to the design problem are encoded, converted to some form the computer can read. One of these forms is the punched card. The information often is transferred from the cards to a magnetic drum or tapes, which can be read by the computer. Problem solutions by the computer can be displayed in various ways. A cathode ray tube, like a television picture tube, may display design solutions which can then be photographed on the face of the tube, lunar landing of a three-dimensional lunar module. Rendezvous of the lunar module with the command module. Earthrise over the moon. Star fields for use in navigation. All of these computer-generated animated drawings were made before the first Apollo manned lunar mission. The computer has since been proved right by history. Another area of computer-assisted engineering involves the processing of data from actual tests, as distinguished from theoretical predictions. For instance, consider the immense amount of aerodynamic, thermal, and metallurgical data in the re-entry of a spacecraft through the Earth's atmosphere. This was the first re-entry test of an Apollo command module. It was unmanned, but recorded by automatic onboard cameras. Approaching the Earth on its return flight from the moon, the spacecraft reaches a velocity of 25,000 miles per hour. As it slams into the Earth's increasingly dense atmosphere, temperatures rise to several thousand degrees Fahrenheit. Due to the blunt shape of the command module, most of this heat is dissipated by waves of air molecules which form and act like a bumper, pushing other molecules of air around and away from the spacecraft. The heat shield must cope with 5,000 degrees of heat as its ablative surface material crumbles, gases, and chars the heat away. Inside the cabin, temperatures remain comfortable. In this first flight test, telemetry relayed the data to a ground tracking station. The station recorded the millions of bits of data in electronic form on analog tapes. The tapes were rushed to the manned spacecraft center, and the data were transferred to digital bits on other reels of magnetic tape. These were then run through the computer. In this case, the computer's output was by a high-speed line printer. After analyses and application, the output data were photographed on microfilm and placed in storage for future reference. So voluminous are such records that another small computer is required to index them and retrieve them when they are needed. Just as spacecraft and systems must be designed, built, and tested over years of research and development with the help of computers, so the men to fly the spacecraft must be carefully prepared and tested. Their every psychophysiological characteristic must be known, analyzed, and evaluated for the responsibilities they must assume during a space mission. From regular and special medical examinations, from biosensor monitoring of each man in a variety of activities, including actual space missions, a store of biomedical and behavioral data is maintained by the computer, capable of rapid retrieval and analysis on that man's suitability for a particular assignment. The pioneering work done in this area at the Manned Spacecraft Center may have far-reaching impact on future computer usage in general medical practice. Astronauts also must spend hundreds of hours in simulators going through every phase of a mission in every nominal and contingency condition imaginable. Training simulators would be inadequate without high-speed interpretive computers, which are used to simulate operational spacecraft computers long before a particular space mission is undertaken. For astronaut training programs, systems planning engineers design both the hardware and the software to make the simulators very realistic. In the Apollo Command Module simulator, most spacecraft systems are represented. Digital computers perform real-time computations that put trainees into convincing spaceflight situations. The sense of reality is heightened by simulated spacecraft characteristics, flight dynamics, and visual and sound effects from control panel lights to jet and rocket noises. The Lunar Module simulator is also an all-digital simulator with 3 computers using coordinates based on math models to simulate the spacecraft and the lunar landing phase of a mission. As in the Command Module trainer, simulation of the primary guidance, navigation, and control system is a most significant part of the training procedures. In the Lunar Module itself, the controlling element in the system is an onboard digital guidance, navigation, and control computer.
Your code numbers. Keep receiver off. There will be no comp check. All personnel assigned emergency phone.
By the time a manned space mission is launched, flight crews and ground support crews have flown the mission hundreds of times, thanks to the computerized simulators. Pre-launch checkouts at the Cape involve many weeks of computer-assisted countdowns. The launch itself would not otherwise be possible.
10, 9, 8, ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commenced. Liftoff. We have liftoff.
At liftoff, as the spaceship clears the tower, the Mission Control Center in Houston takes over command of the flight. The flight director's most valuable resource is the real-time computer complex, one of the largest computer assemblages in the world. Here is some of the computing equipment that calculates flight paths and solves other problems of the space mission on a real-time basis. When necessary to keep the guidance system up to date, the solutions are transmitted to the spacecraft and fed into the onboard computer. Computer-driven data displays reveal the spacecraft's quickly changing location, velocity, and other conditions derived from tracking the spacecraft and communicating with the crew.
Roger, the S-band pointing is pitch minus 22, yaw plus 8. Burn time is 10.3. Roger, Houston.
The actual landing on the moon depends on computerized readings of remaining fuel and altitude.
50 feet. We're in good shape, Chief. 3 feet per second, 40 feet, 3 feet per second, 30, 3 feet per second, looking great, 20 feet, 10, 3 feet per second, contact now. 2, stop, brake, pro, auto. We're on the surface.
While on the moon, astronauts perform active seismic experiments and emplace scientific instruments such as seismometers, magnetometers, and ion particle detectors. Voluminous data are transmitted to Earth from these instruments, which make up the various stations of the Moon's expanding science network. The data are interpreted with the help of computers. After a mission returns safely from the Moon, computers are also indispensable. Inside the Lunar Receiving Laboratory, Moon rocks and soil brought back by the lunar explorers are studied and subjected to preliminary analyses with the help of computer-controlled instrument systems. Remote terminals are set up to permit the antiseptic removal of data from the laboratory and to enable the investigators to use outside computers in their work. Computers are used to identify and classify moon matter and to reduce the data detected by such lunar lab instruments as radiation counters, gas analyzers, mass spectrometers, and electron microscopes. Information processing at MSC is not all related to the Moon and outer space. Systems also are devised for the most efficient business management of the center, whether it be a computerized system to record, remember, and report on books checked out at the technical library, or the computerized magnetic tape library of more than 40,000 tapes. Other computerized operations at this remarkable one-of-a-kind city of space control and prepare paychecks, warehouse inventories, and even inventories of scientific and technical skills to ensure the fullest utilization of the space program's most valuable asset, its people. Another program using computers at MSC is that of Earth Resources. This program uses aircraft to test and develop cameras and other sensors in studies of the Earth. Photo enhancement and pattern recognition of data gathered from such flights are two computerized techniques. The computer draws and color codes various crops growing in a large mapped area of the Earth's surface. Corn, rye, and barley are shown. Similar techniques are used to reveal areas of plant disease, forest fires, underground rivers, and other surface phenomena. Earth resource studies by aircraft and computers are valuable today in their own right and are also contributing to the development of scientific tools for vast studies of the Earth, the Moon, and the planets by manned spacecraft of the future. Skylab, space shuttles, space stations, and eventually spaceships to carry men to Mars. The computers at the Manned Spacecraft Center are truly our keys to the future.